Okay, so we're going to be going through your sample questions for the AP Physics 1 exam, the one we gave you for spring break, which is turned into Spring Deluxe. Okay, so for the first one, it says an object is moving through a positive x direction while the net force is directed along the x-axis and exerted on the object. The figure above shows the force as a function of position. What is the net work done? All right, so what we do is we have a box or something, and we have an arrow going this way. And we need to know the work. Well, there's a formula for work. Work is equal to force times distance. So we need to know what force times distance is. This x-axis is force. This x-axis is distance. Force times distance is the area underneath. So we've got this area here, we've got this area here, and we've got this area here. Now that's a negative area, so basically the two triangles are going to cancel each other out, and we're left with just this box here. So force times distance is going to be right there. Nice. For this one, the diagram shows a top view of a child of mass m on a circular platform of mass 2m rotating counterclockwise. Assume the platform rotates without any friction. Which of the following describes an action by which the child will increase the angular speed? So we're looking for that of the platform system and gives the correct reason why. Okay, so the child moves towards the center of the platform, increasing the total angular momentum. No, momentum will always be conserved, so it's definitely not that one. And for the same reason, it can't be this one, because momentum's always conserved unless you're having an external torque or something like that, but we're not doing that here. Now, the other question is, are they going to move towards or away from the center, decreasing the rotational inertia? Well, it's going to be towards the center. Right? This is just like we did in class when you pulled the weights in on the turntable, you spin around faster. It's the same exact thing. It's just you're not changing the momentum, you're changing the moment of inertia. For here, the figure shows force exerted on block, slide, horizontal surface. Gravitational force is 40 newtons normal, and the frictional force is to the left. Coefficient is 0.2. What's the acceleration? So this is 0.2. So what we're going to do is figure some things out. We know the force of friction is equal to mu times your force normal. So force normal is 40. 0.2 times 40 is equal to 8. So that's 8, but it doesn't want that. It wants the acceleration. So here's a classic F is equal to ma. Have you heard that one before? So this is going to be 8 newtons, and this is going to equal the mass. Well, we don't know what the mass is. Well, we do, because this is the weight. So this is going to equal mg. So if we do the cheap way, we can just say the mass is 4 kilograms, right? Because gravity is equal to 10. Oh, I know. Times A. So 8 divided by 4, it's going to be 2. And it's going to go to the left. It's going to go to the left because that's the way this force is pointing. Because, yeah, it's a direction. All right, so for this one, a student on another planet. So we don't know what gravity is. That's all they're trying to say. Has two identical spheres of mass 0.6 attached to the ends of a rod of negligible mass. The student gives an assembly of a rotation of vertical plane and releases it so it falls. Sensors record the vertical velocity of two spheres, and the data shown the velocity as a function of time. Another student was able to calculate the assembly's angular speed and change in linear momentum of the center of mass between 0 and 0.3 seconds. Which of these quantities can be determined using the graph? So which can we figure out doing the graph? All right. So let's think about it one by one. Can we figure out the angular speed? So this is how fast it's turning. Yes, we can figure out its angular speed, because as it's turning, it's going to go through cycles. So if we start here and we go to here, that's one wavelength. So this is one revolution. We don't need to do anything else, but we can figure out angular speed. Now, it doesn't mean A is right necessarily, but we know that. All right. Change in linear momentum. So can we figure out the change in linear momentum? Well, we know how fast the center of mass is moving, right? Because we know that it's moving this way, so we can know its acceleration, but there's a problem. Oh, we do have each mass. Never mind. So we do have the acceleration. We do have the total mass, because we don't care about the thing in the middle here. So the change in momentum is going to equal the mass times the change in velocity, and we know the changes in velocity, so we can figure out both of them. See? Awesome. All right, next one. A block of known mass is hung from a reel spring, constant of oscillating vertically, so it's bouncing up and down. Which of the following is measured quantities to determine whether the net force equals the vector sum of the individual forces? So we want to make sure the net force equals the individual forces. So there's two forces here. There's the spring force pulling up, and then there's gravity pulling down. They want to make sure the net force equals those two together. So what do you have to know? Well, to figure out what the net force is always going to be found using acceleration, right? So you got to know acceleration. And if you want to make sure that it equals the sum of the individual forces, you're going to also have to know the spring force. We already know what the mass is. Here it says that. So we have to know the spring force. Spring force is going to equal K times X. So we have to know what X is, the position. We already know the spring constant, tells us right there. So we got to know the acceleration and position. Do we need to know the velocity? No, because we only care about forces and we don't care about velocity about that. So that's that. All right, block A and B hang from a light spring, pass over a pulley. It's attached to block B, a new horizontal frictionless table shown above. Students determine the mass of block B. That's what we're looking for from the motion of the two block system after it's released from rest. They plan to measure the time that block A takes to reach the floor, right? So they're going to figure out the time there. The students must also take which of the following measures to determine the mass of block B. Okay, well, if we know how long it takes, well, let's think about it. If we wanted to figure this out, what we'd do is we'd figure out the acceleration, right? Well, if you want to figure out the acceleration, it's starting from rest, so you don't need to worry about that. We know the time because they're already decided about that, but you need to know the distance here because you would use the second equation, that d is equal to v0t plus 1/2 at squared. You'd know this was 0, so this would cancel out. So you'd figure out that, but you need to know the distance to figure out the acceleration, because you know the time already. So we need the distance, so it's not this one. All right, but that'll only tell us the acceleration. So once we know that, then you're going to have to do F is equal to ma. The force pulling is going to be, I'll call it big A. What's the mass of block A? Should put ma? Yeah, it's fine. Times G is equal to mass of B plus mass of A times the acceleration. So we know what the acceleration is because of this step here. But we also have to figure out one of the other two masses. So if you want to figure out the mass of block B, you're going to need to know the mass of block A as well. So it's not just that one, only the mass of block A and the distance it falls. So that one looks good. What do they add here? Radius of the pulley? Nah, we don't need that. Because it's a light pulley, so it's massless, basically, for us. And that's that. So let's see. Two objects are released from rest at the top of the ramps, the same dimensions. As shown in the figure above, the sphere rolls down without slipping. Whee! The small block slides without friction. Whee! Which object reaches the bottom of the ramp first? Easy. The block is going to reach it first. Not because of that one, but because of this reason right here. because it does not have any rotational energy. So remember, your potential energy is going to equal your kinetic energy at the bottom. Whereas in this one, your potential energy is going to equal your kinetic energy plus your rotational energy. Now, because you have to split it between the two things, you're going to have less kinetics, so you're going to be moving slower, so it's going to take longer. This is just like the video we watched where you rolled down all those different cylinders. All those different cylinders took slightly different amounts of time depending on if they were hollow or not. This is the exact same thing. Two blocks, mass M and 2M, are initially at rest in a horizontal frictionless surface. The force F is exerted individually on each block shown above. The graph shows how it varies with time. Which block has the greatest power? So we're looking for power here. All right, there's a formula for power. Power is equal to work divided by time. But we actually want a variant of this, because remember, work is force times distance over time. Distance divided by time is equal to force times velocity. Now, between these two blocks, they're both getting the same force, right? So we don't need to worry about the force part of this. But the velocities are going to be different because they'll have different powers. Which block will have the higher velocity? Well, the smaller block, because it will accelerate faster. So it's going to be the block with mass M. Ta-da! The moon is in an elliptical orbit around the planet shown above. Point A is the moon, has a speed UA, has distance RA. At point B has UB. Which of the following explains a correct method for determining the distance of the moon to the planet at point B in terms of the given quantities? All right, so how are you going to figure out this guy right there? That's RB. So we know what this one is RA, and then each one of these has a speed. They used U for some reason. All right, so do you want to use conservation of angular momentum because gravity force is exerted by the moon? Do you want to use that because the gravitational force is always directed towards the planet? Or do you want to use conservation of energy? Well, I think this one's the hardest one because this one's very ambiguous, strange, but we did this before. What we're going to use is conservation of energy because what we do know is each one of these positions has a particular potential energy, or this is going to be the big U, G, and that's going to equal plus the kinetic energy is going to equal the other spot here. All right, so remember this one is going to be the negative G M over R, and then plus K is 1/2 mv squared is equal to, it's going to be the same thing, G M over R plus 1/2 mv squared. Now these v's are different v's. One of them's for B, one of them's for A. The same thing for these r's down here as well. Okay, so we're going to use conservation of energy, just like we did back in the day. But why? Is it because the gravitational force exerted on the moon is always directed towards the planet? Or is it because the gravitational force exerted by the moon on the planet is the same as the exerted on the planet on the moon? Well, let's look at our equation here. Are we doing anything where it's directed towards the planet? No. This would be if you wanted to do something with centripetal force. So this would be if you were doing something like A is equal to V squared over R. But you can't do that for this one because this is an ellipse. When we did this equation, we made sure they had circular orbits, which is a common thing. Well, sort of. They're usually close enough for that. But they're emphasizing the ellipse here, so we can't do that. So that's why we're going to do D. Okay, block 1 of mass M1 and block 2 of mass M2 are sliding along on a horizontal frictionless surface when they collide at time t. The graph shows the velocities of blocks of a function of time. Which block has the greater mass, and what information indicates this? Okay, so which one's bigger? Well, block 2 is going to be bigger. All right. How do I know this? Because what's going to happen for this? We're going to have M1V1 plus M2V2 is going to equal M. I'll call it 3. You know, 1, 2 together. M3V3, right? Now, block 2 changed less than block 1 did. Since block 2 changed less, that means that it's going to have a bigger mass because it's going to change momentum less. So the final velocity is closer to the initial velocity than the initial of block 1 is closer to the final velocity. And that's it. You know, it's the same situation if you have a bicycle that runs into a semi-truck in a head-on collision. The semi-truck is going to change its speed a lot less than the bicycle will. All right, and we know it's a head-on collision because one's negative, one's positive, and they run into each other. All right, let's see the next one. Okay, so how does the kinetic energy compare to the two-block system with the kinetic energy after the collision? All right, well, let's find out. So we're going to have kinetic energy of 1 plus kinetic energy of 2 is equal to, but probably not, kinetic energy of the thing together. So we'll call it 3. So kinetic energy is going to be 1/2 mv squared. So it's just m1. That's all we know. But we know its velocity is 4. So squared is just throw in the 16 plus 1/2 m2 v squared. So it's just going to be 1 times 1 is equal to maybe, so 1/2, and then we got to put them together here. So m1 plus m2 times its v squared, which is going to be 1 again. Okay. So this guy is going to have 8m1 plus 1/2 m2 is equal to maybe, yeah, distribute the 1/2 m1 plus 1/2 m2. So these just cancel out, these don't matter. But obviously this is going to be less than that because you can't have negative mass. So it's less, it's not the same. It's less because the blocks have the same velocity after collision, so some of their kinetic energy was transformed into internal energy. That sounds good, but let's just double check. It's less because the blocks have velocities in opposite directions, so some of the, yeah, it's silly. Kinetic energy doesn't cancel. All right, it's this, oh, hold on. So it's this one because they have the same velocity, so some of the kinetic energy was transformed. So this is definitely an inelastic collision, right? We know it's an elastic collision already. We should have. Perfectly inelastic because they stick together. All right, that's the secret. They have the same velocity, so they stick together. So it's an inelastic, which makes it definitely less. Remember, elastic means kinetic energy is conserved. Inelastic means it's not, and it's because they stick together. All right, let's do the next one. Which of the following is true of the motion of the center of the mass of the two-block system? All right, let's make sure you understand what's happening here. About the center of the mass. So remember, what's happening here is we have block 1, which is the littler one, is moving this way. It's moving fast. Block 2 is moving this way. It's moving slower. So the center of the mass is going to be somewhere over here, right? So it's just going to be average of the two, you know, the weighted average of the two. After they stick together, so the center mass is going to be somewhere over there, but it's just going to be basically the system itself. And this is moving at a constant speed. We'll call it the V3. Oh, wait, we know what it is. It's going to be at +1 meters per second. All right. Well, does the center of the mass not move because the blocks are moving in opposite directions? No, of course not. That's not true. We know that it's moving afterwards anyways. Does the center of mass move at a constant velocity of 1 because there's no friction? Yeah, but we'll come back to that. Does the center of mass velocity start out greater than 1 but decrease to 1 because it's inelastic? No, it doesn't. So remember, the center of mass can't accelerate unless there's a force, right? Because F is equal to ma for the system as a whole. Now, what happens within this system is its own business, but the center of it is going to act as one thing externally. All right, so it's not going to decrease because you don't have any forces on it. Center of mass increases, blocks close together, and becomes constant after collision. No. It's just for the same reason. So the center of them is going to stay constantly moving this way. And that should make sense because this one's moving to the left, this one's moving to the right. This one's bigger, so it's going to push it more this way. All right? And because this one's moving closer, it's going to pull the center of mass this way as well. All right? So the center of mass is going to average out to be +1, which is the same as when they stick together. And that's how it works that way. All right, refer to the following information. A chart is constructed or constrained to move along a straight line. Cart. Varying net force is exerted the cart's velocity v as a function of time is shown in the graph. So this is the velocity graph. There's 5 sections. Which of the following correctly ranks the magnitude of acceleration for the 4 sections of the graph? Okay, so let's look at it. This is a velocity. So remember how acceleration is equal to your change in velocity is over your change in time, which is just your slope. Okay, so this is your slope, hashtag derivative. So in this part right here, your acceleration is 0. This part right here, your acceleration is negative. This part right here, your acceleration is a smaller negative because it's more flat. And in this part right here, it's changing all the time, but averaged out, right? Nice. Your acceleration is going to be some positive number. So, magnitude of acceleration, so AB is the most. Hey, and then you're done because it's right there, and CD is the least. Cool. Hey, and that's that. Next one, for which segment does the cart move the greatest distance? Okay, so for this one, remember your distance is equal to velocity times time. So this is another one where we're finding area because velocity times time. Hashtag integral. So CD is the area of this triangle. DE is the area of this triangle. So let's do this one. So that's 1 second. We'll just count the boxes if you really want. Let's see. This is, well, it's not CD because BC is bigger than that. This is a 3 by 2. So this has an area of 3 boxes, so it's not this one. So it's one of these two, and, well, the first section has all this extra, which is more than this. So I'm going to go with an A and a B right there. So it's the areas underneath the curve, just like in the first question, I think it was. All right, so for this one, during some part of the motion, the work done is negative. Which feature indicates this? So remember, your work is equal to force times distance. So for this one, these have to be opposite signs, right? If you want this to be a negative, you're going to have positive force for negative distance, or negative distance and positive force, or whichever way I said it. So over here, you're traveling positive velocity, so you're still covering positive distance, and you're moving faster and faster, so you're accelerating the same way, for example. Does that make sense? So that would mean there's no negative work here, it's positive work. And then this one, your speed is going up. What's going to happen is for this guy here, this is 0, so there's nothing to worry about there. You're still traveling to the right in the positive direction, but you're accelerating back towards negative. Does that mean that it's D? No, It's not d, because in this one you're accelerating negative as well, but you're covering negative distance. So it's not that the acceleration is negative, it's that your speed is decreasing. All right, because if your speed, this is speed and not velocity, right? So if your speed is decreasing, that means your velocity is going one way and your acceleration is going the other way. And it doesn't matter which way. So you could flip-flop those arrows and it would still be true. So that would mean that your distance, the displacement that you take, is opposite of the force, because the velocity is controlling the distance and the acceleration is coming from the force, basically. So that's why it's B. Figure shows a block on a horizontal surface has two springs whose other ends are fixed to a wall. The light spring is attached to one side of the block, initially lies straight on the surface. As shown, the other end is free to move. There's significant friction. All right, that's significant between the block and the surface, but negligible friction between the string and the surface. All right, so this is friction in this area here, but the string is doing whatever it feels like. Okay, the block is displaced a distance d and released from rest. Which of the following best represents the shape sometime later? Okay, so what's happening is the block is slowing down, but the string is not going to slow down as fast. All right? So a short time later, the block is going to be basically still. Okay? Now, since the block is still, it could be, well, it's not this one, because that would mean the spring that would mean the spring has no friction. It's perpetuating that wave. The wave is going to be pretty unaffected. Now, if you assume this is like really high friction, it's going to go down quick. So it's going to be this guy right here. All right. So what does this mean? Because remember that this other end is free to move. All right. The other end is free to move, so there's nothing bouncing back. All the waves are traveling this way. So this is the first wave. The first bounce up and down is going to be really big. That's why you have a high amplitude here. But this is going to get stickier and stickier, and it's going to go up and down less and less, and that's why you have a damping there. So it's going to get smaller and smaller amplitude. That's why it's going to be C. Two massive positively charged particles are held at a fixed distance apart. When they are moved further apart, the magnitude of their gravitational force changes by a factor of n. So n is going to be a smaller number there, so don't lose track of that, because they're moving further apart. Which of the following indicates the factor by which the magnitude of their mutual electrostatic force changes? All right, easy. So remember, your gravitational force is going to equal big G, 1m 2m over r squared. Your Coulomb's law is going to be a K, and that's going to be Q1 Q2 over r squared. Now the only thing changing is further apart, the distance, the r. Now if you change the r on this one, it's on this guy, it's going to have the exact same effect if you change the r on that one. So it's just going to be n. Now remember, n is actually less than 1 in this case, so don't get confused and look at these ones. You know, it's just n. It's easy like that. All right, the circuit shown has two resistors of resistance R and 2R. The graph shows the total energy E dissipated by the smaller resistance as shown as a function of time. So this graph here is for this guy. Which of the following shows the corresponding graph for the larger resistor? Okay, so for this resistor here, which one of these is going to be for the power? Well, if only we had a formula for power, right? Or energy dissipated. So we know that power is going to be I times V, right? Well, we also know power is the V is going to be the same because these are in parallel. So they have the same V. So the V is not going to change. But if this one has twice as much resistance, it's going to have half the current. So it's going to have half of that. So the power is going to be 1/2 of the other guy. Now, this isn't a graph of power, though. This is a graph of energy, but power is energy over time. And since this one's time, this is just the slope, okay? So this is going to be half the slope, so it's going to get to half the size, so it's going to be C. And that's that. A student connects one end of a string with a negligible mass to an oscillator. The other end of the string is pulled over the pulley and attached to a suspended weight as shown above. When the student finds the standing wave with one antinode, so there's one antinode in this guy, is formed by the string with the frequency is F0. The student then moves the oscillator to shorten the horizontal segment to half. All right, so let's take it piece by piece. At what frequency is the standing wave now being formed? So if there's one antinode, remember an antinode is the opposite of a node. That's the place where it moves the most. So the antinode is going to be right here on the oscillator. So the wave is going to do this. So this guy right here is going to be half of a wavelength, all right? Boom, boom. Now, that's going to be at F0. So he's going to cut the string in half, move the oscillator closer this way, and that's going to give a new frequency. All right? So we're going to use your famous wave equation for here. Now, the speed in the string isn't going to change. The speed is determined by the tension, and since you have the same mass, the tension is going to be the same. So we don't need to worry about that here. So we want something with half of the wavelength, right? Now this was already half a wavelength, but if we just don't think of it like that, we think of it as a full wave. Now we want half of that size. So we're going to have 1/2 of the wavelength we used to have times some multiple of the frequency. Well, if this is going to be equal, you need a double frequency. So it's going to be 2F0. And that's that. All right. There's another way you can think about it too. We did this exact thing with the really long slinky string here. When I was swinging it around, that was the fundamental. And then the next harmonic is going to have half of there. Now to do that, you have to spin it up and down, shake it up and down twice as fast. You're doubling the frequency to half the wavelength. That's that. The figure shows a portion of a periodic wave on a string at a particular moment. The vertical arrows indicate the direction of the velocity of some points. So these are velocities here. Is the wave moving left or right? Ah, easy. So let's look here. So this guy's going up. That means that it'll be the maximum point soon. Well, that means that this maximum point here will soon be over there. And likewise, over here, this one's going down. That means it'll be here soon. So everything's moving to the left. All right? Because that's where they'll soon be. And it's to the left. Easy problem. All right, a radio speaker produces a sound when a membrane called a diaphragm vibrates, as shown above. Person turns up the volume. Turn it up. Which of the following aspects of motion of a point on the diaphragm must increase? So what's going to happen if you're standing there? Is your displacement going to go up, your speed going to go up, both or neither? Now remember, for volume is based off of amplitude of your sound waves, right? Now, your sound waves are longitudinal waves, so they're really doing this vibration, right? They're vibrating left and right, which makes this vibration left and right. Oh, they drew an arrow there. I didn't even notice that. So that's going to be moving up and down with more amplitude. Well, more amplitude means more displacement. But the frequency is not going to change. The frequency is going to stay constant. So it's going to be this, or it's going to be this. Now, if I'm going up and down by this little bit, up and down by this big bit in the same amount of time, that means the speed is going to go up as well. So we're going to have a C for that answer, because it's both of them. Okay, so for these questions, now we've got 2 answers. So fun. The graph below is a short push and then slides with constant friction across the horizontal floor. The graph shows the kinetic energy, so that's your y-axis here, after the push ends, and some unknown quantity. So what could be that unknown quantity? All right, let's take the easy one first. Speed. It's not speed. It can't be speed because your kinetic energy is equal to 1/2 mv squared. So if you have more v, you have more k. Definitely not c. All right, let's do another one. Let's talk about time. Is it time? Well, let's find out. So we need something to relate time and there. So since we have constant friction, we have constant acceleration, right? So the block's not changing size. So we know that V is equal to V0 plus AT, right? Now, this is constant, and it's never going to change, so we don't care about it. This would be a linear graph, but tragically, we have 1/2 mv squared, right? Once we plug this into here, it's not going to be a linear graph anymore, so it's not going to be time. All right, it's going to be these two, and we'll show you why. Distance traveled by the block, it's because of work is equal to force times distance. Now, your kinetic energy is going to be changing by the amount of work done. The more work, the less kinetic energy you have, right? Since this is constant and this is going to increase linearly, this will increase linearly, which means this will decrease linearly. All right, so that's why it's going to be a B, and it has to be this one because, well, as the work goes up, the kinetic energy goes down, right? They're gonna, they add up to whatever the total amount is. So it's B and D. A musician stands outside in a field. Now, I know you're not doing this at this point in time, but that's okay. He's practicing. And plucks a string on an acoustic guitar. Standing waves will most likely occur on which of the following media? All right, standing waves. Well, one of them is really easy. Standing wave is going to be on the guitar string. So when you pluck a guitar, string vibrates back and forth, something like that. All your stringed instruments do this, even a viola. So it's a guitar string for sure. And then after that, is it going to be the air inside the guitar, surround the guitar, or the ground? Well, the ground doesn't have an endpoint. There's not going to be any interference like that. The waves are just going to be going out. So you're not going to have nodes, right? Because that's what your standing waves are looking for, your nodes. You're not going to have any nodes in there, nor are you going to have any nodes in the air surrounding the guitar. So the reason why is, let's pretend that's the guitar. Your waves are going to be doing this, but they're just going to be traveling out. There's no interference. The waves just project. Inside the guitar, however, what's going to happen is that the waves are going to be going back and forth, bouncing off of the walls. This is how guitars and any instrument produces sound. It's by the internal resonance of the box. So that's why it's A and B. All right, a 0.2 kilogram rock is dropped from a lake a few meters above the surface of the water. All right, let's draw a picture for this one. So here's the water. Here's the rock. It's 0.2 kilograms. The rock reaches terminal velocity in the lake after 5 seconds in the water. So it's going to be going, it's going to hit the water, it's going to keep going after 5 seconds, and then it's going to have terminal velocity. All right, that means it's not accelerating anymore, constant speed. During the final 3 seconds, the rock moves at a constant speed. So right after that, it's going to fall for another 3 seconds, and then it's going to hit the bottom of the lake. Which of the following can be determined from the information given? Select 2 answers. All right, so can we figure out the speed of the lake as it enters? No, we can't figure that out. We don't know how high it was dropped from, or how fast it was thrown, or whatever. It says a few meters, so you can't do anything about that. The distance the rock travels in the first 5 seconds of its descent into the water. No, we can't figure that out. The reason why we can't figure that out is it's not free falling once it's in the water. So in this situation, the rock does have a constant weight, And it does have a constant buoyant force as well, but that's not a physics 1 thing, so we can ignore that for now. But there's going to be friction building up, which is what's going to make it have terminal velocity once these two arrows are going to be equal for terminal velocity. But the friction arrow is going to increase, or the friction arrow is going to change as the velocity changes. All right, I don't know if it'll speed up or slow down because we don't know the speed it enters, but so we can't figure anything like that out. The acceleration of the rock 2 seconds before it reaches the lake bottom. 2 seconds before, so it'll be right about there. Well, I know the acceleration. The acceleration is equal to 0 because it's got a constant speed. The change in potential energy of the rock, earth, water system during the final 3 seconds. Well, yeah, because it's got a constant speed. We know the speed. It says 4, right? So this is 12 meters. Since we know that, we know the distance, we can figure out the potential energy, the mgh. We know the m, we know the h, we know the g. So we can figure out d. Ta-da! Last one. In an experiment with 3 microscopic latex spheres are sprayed into a chamber and become charged with those ones. Later, all 3 spheres collide simultaneously and separate. Which are the following possible values for the charges? Okay. Well, this is important for the law of conservation of charge. If we have a +3, if we have a +5, if we have a -3, putting them all together, so our total is going to be +5. That's the charge on the 3 spheres all together, which means that they have to end with a +5 altogether. So +4 -4 +5. Hey, that equals +5. So that is a good answer. +4 plus these guys, +9. So this is a +13. No way. +5 -8 is -3. So this is equal to +4. So nope. +6, which is +12, -7 is +5. Hey, so that's that. And it's okay that they have way more bigger charges here. The reason why it's okay is because, remember, there's separation of charges. So each one of them has a certain number of plus charges. Let's just take this +3 guy, how he started with. He has a lot more. He just has more positives, 3 more positives than he has negatives. He actually has a very, very high number of these guys, and it just adds up to 3 extra. So that's all going to match. All right, now it's time for the fun part, the free response part. So you've got a car of known mass m1 will collide with a second car of known mass m2. The collision will be head-on, and both cars will move linearly before and after the collision. In a clear, coherent paragraph-length response, explain a method for determining whether the collision is perfectly elastic, perfectly inelastic, or neither. If the collision is perfectly inelastic, include at least one possible cause of energy loss. So what we'd have to figure out is how they're going to collide. All right, is it going to be elastic, inelastic, or neither? Now, you don't know which one they're doing. We don't know that because, maybe they're Hot Wheels cars. If you collide 2 Hot Wheels cars together, it's going to collide a lot differently than 2 real-life cars at real-life speeds. So let's talk about those 2 situations. All right, you would put this in a paragraph form, but I'm going to show you in a different way. You could always do both when you're doing the real test here, and who knows how that's going to work, right? So let's talk about elastic. We'll talk here about inelastic. We're talking about perfectly in each one of those. And then here's neither. So for elastic, they're going to bounce off, right? So here's car 1, here's car 2. They're headed towards each other. They're going to collide, and then after that, they're going to bounce off of each other. Boom, boom. All right, so this is kind of like if you had the Newton balls, whoosh, they bounce off each other, or like Hot Wheels cars would probably do that. So how can you tell which one, how can you tell if it's elastic? The main thing for elastic is that the kinetic energy is going to stay constant. So kinetic energy of car 1 plus kinetic energy of car 2 is going to equal kinetic energy of car 1 plus kinetic energy of car 2 post. So we'll call this KE1I, KE2I, KE1F, KE2F, right? And then if you do that and it works, then it's elastic. So that's what you do. So you want to explain a method for determining the collision, all right? So if you're doing elastic, because they bounce off each other like this, the kinetic energy is constant, this is how you'd approach it. For the inelastic means that they're going to stick together. I think there was a question like that. So they come together, boom, boom, they're going to stick together, and maybe one of them had slightly more momentum and it's going to keep going together. All right, so how can you tell afterwards if it's perfectly inelastic? Well, what you're going to know then is if the velocities are the same. This is the same question we had before. So velocity 1 final is equal to velocity 2 final. If those are equal to each other, that would figure out if it were inelastic. All right, and you'd lose kinetic energy in that situation as well. If it were neither, remember, because this is perfectly inelastic. So if it were neither, it's going to do something in between these two situations. All right. So what would happen is that the kinetic energy initial is going to be greater than the kinetic energy final. So that tells us it's not perfectly elastic. And the velocity of 1 final is not equal to the velocity of 2 final. So it'd be both of these situations. So it's not inelastic, perfectly inelastic, and it's not perfectly elastic. It's just something else. Anything in between. It could be 99% inelastic, it could be 99% elastic, or anywhere, or 50-50. All right, so you would explain that in a paragraph, hopefully. But this is the kind of stuff they're looking for. 1, 2, and 3. And then if the collision is perfectly inelastic, what's one possible cause of energy loss? Well, if it were, we lost the kinetic energy. So one possible source would be the work to bend the metal of the car. All right, cars. So as the cars, thinking of real life cars, if you crash into another car, which you shouldn't do at home, what's going to happen is the bumpers are going to bend. Those bumpers are bending because they're trying to take the kinetic energy away from you and the car to slow you down more gradually to do work. And that's what makes it, that's where the lost energy goes. Ta-da. Hey, next one. Each of the 3 graphs depicts the velocity of an object as a function of time. Each graph as a different object is labeled above. For each velocity graph, draw displacement versus time and an acceleration versus time, and give an example of something that can do that. Okay, so each one of these is going to give you 2 graphs. So here's your acceleration and here's your displacement. Each one of these is going to have a time for your x. All right, so remember, acceleration is the change in velocity. So your acceleration is equal to your slope, #derivative. So what's the slope of this? The slope of this is just some number there. And then once you get to this point here, your slope is 0. So your slope is going to be on your axis right there. Ta-da! Okay. Now for this one, remember it's going to be your areas underneath. You can think of it like that if you want, or you can think qualitatively. Where this guy right here, you have an increasing velocity. So that means that your displacement is going to increase as a quadratic, right? You know, just thinking about your kinematic equations here. Once you get to this middle point, you're going to be going at a constant speed. So you can go to a straight line, but these are going to connect smoothly because the speed at the end of this, the beginning of this, is equal to each other. So it's going to change to a straight line. Okay, so what's something that can do this? What's something that accelerates? So you could have a ball going down a ramp, ball going down a ramp, but once it gets to this point here, then it reaches flat ground, reaching the ground. Reaching the level ground. Okay, now if you make mistakes like that on your AP test, just fit it in there. They expect you to go fast. Well, who knows what they expect this year. Okay, so for this one over here, are you feeling the calculus yet? So your acceleration graph, what's the slope? The slope is negative, and it's going to be constant the whole time. So we're just going to do something like that. And then what's your displacement going to be? Well, you've got positive movement that decreases to 0. At this point, you're perfectly stationary, and then you're moving back down, and then accelerating down. So it's going to be something like this. Perfect. Okay, now if you're looking at the picture of the displacement graph, it should be kind of, well, there should be something that jumps out in your mind. There's something that jumps in my mind, and it's just a ball thrown up. Thrown upwards. Right? So constant acceleration, gravity. It's going to accelerate up, then it's going to accelerate down, and this is the path it'll take. Well, not the path, but the y path it will take. All right, for the final one, what's your acceleration going to be? Well, it's just a constant positive value. What's your displacement going to be? Well, if you're constantly accelerating in one direction, it's going to go in a quadratic, something like that. So what's something that does this? A car accelerates constantly. Accelerates, I'm going to say from rest constantly. You know, the more you can show you know what you're doing, the better you are. All right, that's all you have to do for that one. Next one. Diagram above, a spring block system is oscillating on a horizontal flat surface. Part of the surface is frictionless and part of it is frictional. The block starts at rest at position 0. After the block is pushed to the left, compress the spring until it reaches negative 50. All right, so we're going down to minus 50. And then the block is released and allowed to move naturally. So then it would go over here to plus 50. Now this section right here is your rough section that has friction. Okay, so draw a graph of the system's position as a function of time, starting from the moment it's released, and explain your reasoning behind the graph you drew. Be sure to label important values in the graph. Okay, so let's start with a graph. Boom, boom. So here's 0. Well, let's have the bottom be negative 50 and positive 50. We're not going to have to worry about that. And then we should call these in distance. We should label our axes here. Displacement. And that's in centimeters. And this is time. We don't have any real values for the time, so it's okay. When they're doing something like this, they just want you to sketch it. Give you rough guesses here. So we're going to start at 50, and it's going to shoot all the way to 50. Well, almost all the way to 50. You're going to lose some energy. So let's just, say it goes to 45 or something like that. There's no way to know at this point, but we do know that it's going to go up to almost 50. And then it's going to go back down. Now, if we said it was 45 a second ago, it's going to pass through friction on the way down. So it's going to drop to almost where it was. We'll say negative 40. It's just a guess. All right, and it's going to do that again until, I don't know, we'll have one more going up. One more going down. Oops. And then what's going to happen is now it's reaching 30, which means that it's not going to change anymore because there's no more friction. All right, so it said to label important values. So let's label this one. Ooh, I'll change colors real quick. So this is at 30. And then what's going to happen is this one is also going to be at 30. The bottom, negative 30. All right, so then it's going to just continue on forever in that way. Okay. So given that the mass is 2 kilograms and the spring constant is 100, what's the magnitude of work done? Now, I know what you want to do. You're thinking, oh, it's easy. Work is equal to force times distance. But here's the problem. The force is going to be changing depending on the distance because as it moves up, the force changes because of the spring. So you don't want to do it that way. All right? You want to use a different work formula. The other work formula is just the difference in the energies. So we're going to talk about the potential energy from the spring initially, and then that's going to equal any other point. We're comparing this guy right here, that's our initial here, to this guy right here. Now it doesn't matter top or bottom because it's going to be equal on the spring, plus W, because this is less than that. All right, so remember your your spring energy formula is going to be 1/2 kx squared plus 1 equals 1/2 kx squared plus W. These kx's are not the same, or the x's are not the same. So 1/2, I think the constant is 100 times x is 50. Well, but that's in centimeters, so it's going to be 0.5 squared equals 1/2 100 times 0.3 squared, because it's 30, plus W. All right, I'm checking my numbers here. That way I don't have to make you wait. So once you grind these together, you're going to get 12.5 is equal to 4.5 plus W. So W is equal to 8 joules. So that's how much work is done by the friction. All right, moving on. A roller coaster cart rides along the surface tracks as shown. The initial drop, loop, and ascending ramp are all frictionless. The flat portion of the track of the ascending ramp is frictional. All right, so just this part has some friction. We'll deal with that when we get to it. How fast would the cart be moving just before it enters the loop? Easy. So what we know is we know that mgh is equal to 1/2 mv squared. All right, m's cancel out because, it doesn't matter. G, well, I'm sorry, I'm going to cheap out. 10 times, these are in meters, so we're all good here, is equal to 1/2 v squared. So it's going to be 400 is equal to v squared. V is equal to 20 meters per second. Excellent. Now, if you did 9.8, you get something really close. It's 19.8, when they're totally fine with either one. Hey, would the normal force of the cart be greater just after or just after entering the loop or at the peak of the loop? Explain using relevant equations. All right, so let's think about this loop here. So if you just enter it before, the normal force is going to be pointing up. The normal force is going to be pointing up because it's acting as your centripetal force, and gravity is pointing down. At the top, I'm gonna redo it up here. Ooh, so good. At the top, the normal force is pointing down, gravity is also pointing down. So the reason why, which is going to be greater, it's going to be just after entering the loop. You know, it's just like why you feel the heaviest on a swing at the bottom as opposed to at the top. All right, explain why using relevant equations. So you're going to explain why, but the most important thing is your force centripetal is going to equal force normal minus force of gravity at the bottom. And at the top, your force centripetal is going to equal force normal plus your force of gravity. Okay? Which means that your force normal here has to be bigger because you're subtracting gravity from it. And that's it. All right, next one. What's the greatest possible radius for the loop that would allow the cart to still make it through? All right, you have to be careful with this one. You can't just jump to your centripetal equation. The reason why is because as you're going up, you're going to be slowing down. So what we know is we know mgh of here, right? That's that spot, is going to equal here. You know, well, mgh plus 1/2 mv squared. All right, so far so good. Now there's one more piece to this puzzle. What we do know is we do know that your centripetal acceleration is going to be v squared over r, and you have to beat gravity, right? Because your centripetal has to at least match gravity. That's if your normal force was 0 here. So that means that gr is equal to v squared, and we're going to plug that into here. All right, and cancel out m's at the same time. So cancel, cancel, and cancel. So we're going to have gh is equal to, I'm going to plug it in the h's because the h's are different. G times 20 is equal to g times h, which is going to be 2 of the radii, right? Now 1 radius for here, 1 radius for there. Plus 1/2 v squared. V squared is equal to gr. Nice. G's cancel now as well. So we're going to have 20 is equal to 2r plus half of r. So 20 is equal to 2.5 r. So r is equal to 8, right? Yeah, 8 meters, because that's the radius. Okay, so now for the last one, if the coefficient of static friction is 0.2, how long does the segment need to be to allow the cart to come to a complete stop? All right, well, we have to figure out 2 things. We have to figure out how fast the car is going at this spot here, and then what the acceleration is, right? So let's do the velocity first. So we're going to have mgh, once again, that's at the first spot, is equal to mgh plus 1/2 mv squared. So cancel out those m's. Yeah, I know, you didn't need to write them. That's okay. So 10 times 20 is equal to 10 times 10. Yeah, you could have combined those together. Plus 1/2 v squared. That's 200 minus 100. Back to 200. So that's going to be 14.1 is equal to v. Sound good? Square root of 200. Okay. So now we need to know, if you have this velocity, what's the acceleration? Well, we got to figure out the friction first. So we know that F, force of friction, is equal to mu times your force normal. That's the only force, so that's going to be m times a for force of friction, right? It's going to be 0.2 times your normal force, which is going to be mg. So m's cancel out. So your acceleration is 0.2 times g. So the acceleration is equal to 2 because gravity equals 10. Okay, now we're going to put these together here. We're going to have our v squared is equal to v0 squared plus 2 times a times d. So our v squared is going to be 0 because we're going to a stop. Our v0 squared is the 14 squared, which is 200 even, plus 2 times acceleration is negative 2. Don't forget, because the acceleration is going the opposite way as the velocity, or as the distance here. Times the distance is what we're solving for. So kick this to the other side. 200 divided by 4 is going to equal 50 meters. Ta-da! And that's it for that one. Next. Okay, so the last one. So the above circuit contains a battery voltage V, 3 resistors, R1, R2, R3. As part of an experiment, students given 2 measuring devices, a voltmeter and an ammeter. The first can be used to measure voltage, the second can be used to measure current. Here's what they look like. All right. So in terms of the known variables, what is the voltage lost in passing through the first resistor? So we are talking about that one there. All right, so to figure that out, we'll start up here. We have to figure out what the current is. To figure out the current, we have to figure out what the resistance is. So let's do that. The total resistance for the circuit, we have to start with these two guys. So we're going to have 1 over R2 plus 1 over R3. And then we have to add that to the one in series, to the first one. So R1 plus 1 over R2 plus 1 over R3. Hey, that's the total resistance. Now we got to figure out the current. To figure out the current, we use V is equal to I times R. We know what V is. V is the volts. We know what R is because we just figured that out. We're solving for current. So current is going to be V divided by R. Now V is just V, and R is going to be R1 plus 1 over R2 plus 1 over R3. Wasn't that fun? And we're still not done yet, because now we need to figure out the voltage for him. So we're going to go back to V is equal to I times R. Now, he doesn't have the same voltage as the battery, so the voltage is different here, but the current is going to be the same because he's in series. So V over R1 plus 1 over R2 plus 1 over R3, right? Close that off. Times the resistance, all right? So times the resistance for just him is going to be just R1. And so that's it. Don't need to simplify it. Just leave it the way it is. It's fine. All right, for part B, draw a diagram showing how you would integrate the voltmeter into the measure of voltage lost in R1. Easy. So we're going to take this guy, put a voltmeter in right there. Ooh, it's a V. Perfect enough. Explain the reasoning behind. Voltmeters are in parallel. Voltmeters are in parallel. Why? So they have equal voltage. Nice. All right, for the next one, part C. Draw a diagram showing you integrate the ammeter and to measure the current passing through the resistor labeled R1. Okay, well we could put it in lots of places and I'm all out of room on the left. I'm going to put it right here. So here's the ammeter. And then what we're going to do then is we're going to take out this wire. Well, you could just put it on the wire if you want, but you know, any way that represents that. Okay. You could also put it right before, right after. I'm kind of out of room. All right, why would you put it there? Ammeters are in series. Why are they in series? So they have equal current. All right, for part D. Hey, what would be the ideal resistances for each one? Explain why each would be ideal for that device. Okay, well, let's talk about voltmeters first. Voltmeters should have infinite resistance. All right, why should they have infinite resistance? So no current passes through them. All right, so, thinking about it like this, current's coming in this way, it should all go through the resistor. It shouldn't go through the voltmeter at all. For ammeters should have zero resistance. All right, why? So there's no voltage drop. So there is no voltage drop. All right, so they don't lose any voltage as the current travels through them because the current has to pass through them. Hey, and that's all. Easy money, right? So we'll look at doing the next one later. All right, all done.